Welcome back to Physics 142 online. We're now going to discuss what happens when more than one wave is traveling through the same medium at the same time. And in order to understand what happens, we'll use what physicists call the superposition principle. It sounds a little bit fancier than it really is, but what it really is telling us is that when two or more waves travel through the same medium at the same time, the net wave function at all times is just the sum of the wave functions of the different waves. Could be two, could be more. One consequence of this is that two waves that are passing through the same medium do not affect one another's shapes, and they pass through each other undisturbed. And so mathematically, the superposition principle is nothing more than just telling us that the total or the net wave function, as a function of position and time, is just the sum of the two wave functions of the two waves. And if we have more than two waves, we would just continue to add terms. Physicists like to say that these waves that are passing through the same medium interfere with one another. And there's two possibilities. If the resultant wave, the total wave, has an amplitude greater than either one of the two individual waves, we say that the interference is constructive. But, on the other hand, there may be times where the amplitude of the net wave is smaller than either individual wave, and in that case, interference is destructive. So let's do an example mathematically to see how this works. We can easily find the sum of two harmonic waves that have the same amplitude, frequency, and wavelength, but differ only by having a phase difference. So if we look at y1, it has the familiar a cosine kx minus omega t, which is a traveling wave, and y2 is also a traveling wave. The only difference is there's a phase angle of pi, which shifts it by an amount of pi radians from wave function 1. So what happens if these two waves travel through the same medium together? By the way, we say that these two waves are out of phase by pi because the argument of the cosine function is sometimes called the phase of the wave. So when we add those two together, we can factor out the amplitude A because they have a common amplitude. And what we see is we just have the sum of two cosine terms with slightly different arguments. So now we're going to use the identity, which you can find in the back of your textbook, that tells us cosine A plus cosine B is twice the cosine of half A minus B times the cosine of half A plus B. And so if we do this, where little a is the term kx minus omega t, and little b is the term kx minus omega t plus pi, when we simplify this, we end up with the net wave that has an amplitude 2a, and then it's got cosine of negative pi over 2, and finally cosine kx minus omega t plus pi over 2. And notice the interesting fact that because we have this term cosine of negative pi over 2, it has the value 0. And therefore the total wave is equal to 0. And so what this means is we have an example of complete destructive interference, where not only is the amplitude of the net wave less than either individual wave, it's actually equal to 0. And when we have complete destructive interference or complete constructive interference, there are usually very striking phenomena that we can observe. So now let's look at a slightly different example of superposition by considering standing waves on a string. And the basic idea here is that when two identical waves travel in the same medium but travel in opposite directions, we end up with a totally new kind of wave pattern. So let's consider a stretched string that's fixed at both ends, and so we cause a wave to move in the positive x direction along that string. So y1 is a cosine kx minus omega t. This is a wave moving in the positive x direction, and when it hits the fixed end, that wave will reflect back. But because it reflects back, actually it flips over, and so the wave that's reflected back has the same amplitude, but it's got a minus sign out in front because the wave has been inverted. And also, because of the fact that it's moving now in the negative x direction, there's a plus sign in the argument. So this is exactly what happens on a stretched string when we pluck it. We send a wave down in one direction, and then part of the wave is reflected backwards, and these two waves, if we continue to cause the wave motion to happen, these two waves interfere with each other. So let's see what happens when we add them together. We can use a slightly different identity, because in this case we've got a cosine term that has a factor a, and then another one that's got a factor negative a, and so we actually have the difference of two cosine terms if we add these two together. So we want to use the identity that gives us the difference between two cosines. So the total wave, which is just the sum of y1 and y2, when we use this identity and simplify, gives us 2a sine kx times sine omega t. And what's very interesting about this resultant function is that the x and the t dependence is no longer in the same argument for a cosine or a sine function. They actually split up. So as a result of that, this is not a traveling wave, because the dependence of the wave on x and t is contained in two separate terms. As a result of this, there will be fixed points along the string where either nodes or antinodes appear, and those positions will not change with time. In other words, we're going to find out in just a second that there will be specific values of x along the string where the function will go to 0, and it will be 0 no matter what the value of time is, and those will be the position of nodes. As a result of having the nodes and the antinodes always have the same locations, this wave pattern does not move along the x direction, and as a result we call this kind of a wave a standing wave. So many musical instruments have strings held in tension and fixed at both ends, and when these strings are plucked or excited with a bow like in a violin, standing waves are produced. And I think if you followed the explanation that I just gave, you can explain physically why that is. So the string, if it's fixed at both ends, x equals 0 and x equals L, the fact that it's fixed defines the boundary conditions. Basically what they tell us is that the string at those two positions cannot move. It's completely fixed. So the y value in our standing wave function at x equals 0 is equal to 0. And the same thing is true at x equals L. So the two endpoints have to be points of nodes where the string cannot vibrate at all. So when those two boundary conditions are fixed, they, along with the length of the string, determine the resonant frequencies of the allowed standing waves on the string. There's more than one possibility, but all of the allowed standing waves have to have nodes at the two ends. So here's a picture showing the x and y directions, and imagining that we have a string that's fixed at x equals 0 and x equals L. So here's our standing wave function, and you can see that when x is equal to 0, this function will always be 0 no matter what the value of the time is, because the sine of 0 is equal to 0. However, we also know that that has to be true at x equals L as well. So let's find out what that means. We'll take this wave function, plug in x equals L, and set it equal to 0. So we've now used the second boundary condition for the x equals L end of the string, and we know that it's not something that has to be 0 just at some special time, but it's got to be 0 at all times, because that end of the string is fixed. So what that means is, in order for this to be 0 at all times, the sine KL has to be equal to 0, and that will only happen for special values of k. So if sine KL is equal to 0, well, we know that KL, in order for that to be true, has to be some integer multiple of pi. So we'll call it n times pi, where n is an integer. And now, remembering the definition of the wave number k, we have the following. K is 2 pi over lambda. So 2 pi over lambda is now, times L, is n pi. And then solving for lambda, we'll put a little subscript n on there because the value depends on the integer n. So the wavelengths for standing waves on a string, when the string is fixed at both ends, is equal to 2L over the integer n. So these standing waves, if they have the frequencies that are given in the box here, if they have wavelengths given by this result, they have to have frequencies that are given by the familiar formula F equals V over lambda. And so if we plug in lambda is 2L over n, we find the general equation for the resonant frequencies or the standing wave frequencies of a stretched string. F is equal to the integer n times the wave speed on the string divided by twice the length. Now, as useful as this formula is, I always find it to be most helpful, rather than memorizing a formula, to be able to draw the stretched string and sketch the different standing wave patterns. And we'll do some examples of this in class. And that's something that I'll want you to be able to do on homework problems, on quizzes, on exams, is not only to calculate these frequencies or to calculate the wavelengths that go along with them, but to be able to draw the standing wave patterns. We'll get some practice doing this in class, and I hope this has been a useful introduction. See you soon.